Want to impress an interviewer with dynamic programming that feels like magic? Maximum profit in job scheduling is the famous weighted interval scheduling problem. Heavy hitter and an essential in Pattern Mastery 100. Get this right and you'll show mastery of DP, sorting, and binary search in one clean solution. Let's nail it with basics so your story and code are airtight. Let's break it down. We're given 3 arrays: start time I, end time I, and profit I, for jobs. We must pick a set of non-overlapping jobs to maximize total profit. If a job ends at time t, another job can start at time t. That's not an overlap. Output is the maximum achievable profit. Let's assess it. Brute force over subsets is exponential. The classic optimal approach is DP plus binary search after sorting by end time. Let jobs be sorted by end. Let DPI be the max profit using the first I jobs. For job I, find j equals index of the last job that ends less than or equal to start I, using bisect underscore right on the sorted end times. Transition. Skip job I DP, I1, take job I DP, j plus profit I. Then DPI, equals max skip, take. Complexity. On log n. Sort plus per job binary search, space on. Here is the structure. Zip, start, end, profit, and sort by end. Maintain arrays ends and DP where DPI means the best profit using the first I sorted jobs. For each job I, binary search the last compatible j using bisect underscore right ends, start I. Update DPI, equals max DPI1, DPJ, plus profit I. Return DPN. Now let's try to implement it using solution 1. Efficiency overview. The time complexity is on log n, and the space complexity is on. We combine start time, end time, and profit into a single structure and sort jobs by start time so future searches are efficient. This array allows us to binary search the next job that doesn't overlap with the current one. This helper finds the earliest job whose start time is at least the given target end time. This recursive function computes the maximum profit starting from job index I. At each job, we either take it and jump to the next valid job, or skip it and try the next job. We store results so the same subproblem is never solved more than once. We start the recursion from the first job to compute the maximum total profit. And that's how this algorithm works. It first sorts jobs and prepares fast lookups, then recursively decides whether to take or skip each job while jumping efficiently using binary search. Efficient, simple, and elegant. Check number 1. Let's test our function using this input. Each job has a start time, an end time, and an associated profit. The goal is to select non-overlapping jobs so that the total profit is maximized. We consider jobs in order of their end times and decide, for each job, whether we take it and add its profit to the best profit achievable before its start time, or we skip it and keep the previous maximum profit. For this case, job 1,3 gives a profit of 50. Job 3,5 gives 40, and job 3,6 gives 70. Both can start after time 3. The optimal combination is 1,3, 3,6, giving 50 plus 70 equals 120. And that's exactly what our program returns. So, our implementation is correct. The algorithm efficiently chooses the best non-overlapping job combination and maximizes total profit, accurate and optimal. Now let's try to implement it using solution 2. Efficiency overview. The time complexity is on log n, and the space complexity is on. We bundle each job's start time, end time, and profit together and sort all jobs by start time to enable fast lookups. This array lets us binary search for the next job that doesn't overlap with the current one. DPI represents the maximum profit achievable starting from job I. The extra slot handles the base case beyond the last job. This helper efficiently finds the earliest job whose start time is at least the current job's end time. For each job, we decide whether to take it or skip it and store the best possible profit. The optimal profit starting from the first job is stored at DP0. And that's how this algorithm works. It first organizes jobs and prepares fast searches, then builds the maximum profit bottom-up by choosing between taking or skipping each job. Efficient, simple, and elegant. Check number 2. Let's test our function using this input. All jobs start at the same time, but they end at different times and offer different profits. Since all jobs overlap with each other, they all start at time 1, we can only choose one job. So the decision comes down to picking the job with the highest profit. In this case, job ending at 2 gives profit 5. Job ending at 3 gives profit 6. Job ending at 4 gives profit 4. The best choice is the job with profit 6, and that's exactly what our program returns. So, our implementation is correct. The algorithm correctly handles overlapping jobs and selects the most profitable option, efficient and reliable. When you want to prove you understand dynamic programming beyond the basics, maximum profit in job scheduling is the problem to showcase. It's a clean blend of DP, sorting, and binary search that feels like algorithmic elegance in motion. Let's do a recap. We're given start times, end times, and profits for multiple jobs. The goal is to choose non-overlapping jobs to maximize total profit, simple conceptually, but tricky in execution. A brute force approach would explore every subset of jobs, but that's far too slow. The optimal solution uses dynamic programming with binary search, sorting jobs by end time and quickly finding the last non-conflicting job for each new one. The plan: sort all jobs by end time. Use a DP array where DPI holds the best profit up to the ITA job. For each job, binary search for the last compatible one and decide, skip it or include it for a higher total. We built the DP with sorted jobs, applied binary search for compatibility, and confirmed that the algorithm ran smoothly on LeetCode without any errors. All test cases passed successfully, validating both performance and correctness of the DP plus binary search approach. The key lesson: optimization comes from combining ideas. Sorting gives order, binary search brings speed, and DP ensures memory of the best results. Together, they turn a hard scheduling challenge into a clean, efficient solution.